Before we get started, I wanted to let you know that today's episode is brought to you by Space the Longest Goodbye, available now on the PBS app and YouTube. So check out the link below. We are the middle children of history, born too late to explore the Earth, born too early to explore the universe. To partially quote someone on the internet whose wisdom is only matched by their anonymity. In the far future, we may have advanced propulsion technologies like matter-antimatter engines and compact fusion drives that allow humans to travel to other stars on timescales shorter than their own lives. But what if those technologies never materialized? Are we imprisoned by the vastness of space, doomed to remain in the solar system of our origin? Perhaps not. A possible path to a contemporary cosmic dream may be to just build a ship that can support human life for several generations, a so-called generation ship. Faster-than-light travel is almost certainly impossible. So says Einstein's special theory of relativity, and we rarely win when we bet against Einstein. That sounds like bad news for the galactic future of humanity, given that the Milky Way is 100,000 light years across, and there are relatively few stars in what most would consider to be a reasonable commute. But that doesn't mean we can't reach for the stars. If we could build spacecraft capable of reaching 80, 90, even 99% the speed of light, then relativistic time dilation would slow the clock of the spacecraft relative to Earth's. At these speeds, a single crew could reach an interstellar destination up to hundreds of light years away within their own lifetimes. But such speeds would require some pretty out-there propulsion methods like matter-antimatter engines, compact fusion reactors, or even black hole drives. And even if we eventually do build such devices, there are a whole range of dangers that uniquely arise when traveling through the cosmos at such high speeds, as we've discussed previously. So, what if it turns out that we have to travel the slow road? What if it proves impossible to send humans any faster than a tiny fraction of the speed of light? Or, what if we decide that we really need to leave Earth ASAP using technology that we at least understand today? Okay, here's the scenario. Something is coming. It could be a comet impact, or catastrophic climate collapse, or the Trisolaran fleet. Whatever it is, there's enough of an existential threat that we decide to ensure the future of our species by trying to settle another world. Quite naturally, NASA tasks PBS Spacetime with planning a mission to settle Proxima Centauri b in the Alpha Centauri system. This is the closest known exoplanet to Earth, a mere 4.2 light years away. To keep things simple, let's pretend that we discovered that Proxima b is already habitable, so all we need to do is get some people there in good condition. We only have a few decades to make this happen, so ultra-advanced propulsion is out of the question. We launch whatever we can throw together in around 30 years. The fastest ship we could conceivably hope to build might reach speeds of 10% that of light. That's a 42-year journey. Launch a crew in their 20s and they'll arrive at retirement age. More likely, our craft will travel much slower, so no crew that starts the journey will live to see its end. Assuming that cryogenics won't be 100% reliable within decades, which is a pretty fair assumption, it sounds like we need to plan for a mission in which multiple generations of humans are born, live and die en route, and that landfall is made by the descendants of the launch crew. It sounds like we need to plan for a generation ship. There are lots of decisions to make in how we do this, but remember our constraint. It has to be something we can plausibly launch in 30 years. We're going to need to choose a propulsion system, a crew size and composition, life support systems, and finally, we need to ensure the mental, social, and cultural well-being and stability of this group. Starting with the propulsion method, this determines the speed we can travel, the potential size of the ship, and so the size and number of generations of the population we need to sustain. The fastest vehicle ever built by humans is the Parker Solar Probe, which accelerates by blasting a propellant, hydrazine in this case, using electrical power, although it was really more the gravitational assists that enabled the Parker to reach 700,000 kilometers per hour. If we could scale up this tech to something large enough to carry lots of humans, then at this speed we could get the crew to Proxima b in 6,300 years. It's like 200 generations, and roughly the length of recorded human history. It's difficult to imagine that nothing would go wrong in that much time, but we're also pretty sure that we can get a ship to this speed, so we should see if this timescale is at least feasible. Also, this is the speed assumption made by French scientists Frédéric Marin and Camille Bellouffi in a series of studies, and we'll be coming back to their conclusions regarding a trip of this length. We'll also consider a much faster craft, one propelled by nuclear fusion, smashing light elements together to form heavier elements plus lots of energy, just like our sun does. We haven't yet managed to build a commercially viable fusion reactor, let alone the sort of compact reactor we need for a spacecraft, but there is a fusion technology that we've thoroughly mastered, and that's the thermonuclear explosion. There are various concepts for spacecraft that accelerate under a series of fusion pulses, aka explosions, rather than sustained fusion reactions. These vary in sophistication from the more advanced internal confinement engines of Project Daedalus to more achievable, if scarier, proposals where you literally detonate thermonuclear explosions behind the craft, like Project Orion or the Ensman starship, or into a forward sail like the Medusa design. Top speeds for some of these have been estimated at 30% light speed, but that's highly optimistic. A little under 10% is more realistic for a mature version of this technology. For us, with our limited timeline, we're going to assume we can get to 3% light speed. That's around 50 times faster than our conventional drive, so it gets us to Proxima b in a mere 140 years, just 4 or 5 generations. So, today, we're going to plan towards these two travel times, 140 years if fusion pans out, and 6,300 years if not. We'll have teams working on both, and you can think of these as representing the extreme boundaries of what we can achieve in the little time that we have. The next decision will influence all of the choices that follow. How many people are we sending? This determines the size of the ship or ships and the resources we need to bring. Perhaps the most important factor determining the population size on a generation ship is the issue of genetic diversity. There are two aspects to this. How many people are needed to ensure a healthy multi-generational crew during the journey, and how many are needed to healthily populate a new planet? A 6,300-year journey means 200 generations, give or take. If the genetic diversity of the starting population isn't sufficient, there'll be genetic health issues en route. Marin and Bellouffi explore this question in a 2018 paper. They use Monte Carlo simulations to calculate the minimum number of humans that would be needed to avoid many of the potential genetic pitfalls, also accounting for various forms of misfortune, such as random disaster eliminating a third of the population, different infertility rates, and even an overall chaotic factor intrinsic to any human exploration. From all of this, they came up with the minimum numbers needed to achieve sustainable population during the journey. They conclude that we need to launch with a crew of at least 100, who will multiply to a population of 500, and that's the level we need to support for most of the journey. How big a ship does it take to comfortably carry 500? Well, SpaceX's Starship is supposed to be able to carry 100, so the equivalent of 5 of those, at least. However, that doesn't include the space needed for systems to support 500 lives long term. For that, we're definitely going to need a bigger boat. Missions around the solar system don't need to be luxurious, but centuries or millennia long trips to Proxima b will need some home comforts, like gravity. Living in zero gravity or microgravity has clear negative effects on health, with the most well documented being on bone density. To avoid our travellers reaching Proxima b as Wall-E-esque gelatinous blobs, we need artificial gravity. We've discussed previously how this could be done. There really is only one way, and fortunately it's not that complicated. The ship's habitats need to be spun in a circle to give 1g of centrifugal acceleration, perfectly mimicking Earth's surface gravity. There are lots of designs for centrifugal artificial gravity, but the simplest might be a rotating ring habitat. A 100-meter radius ring would need to rotate 3 times per minute to replicate Earth gravity. That seems not completely crazy. So let's just move on. The next step is to feed our crew. Another study, led by the French team, finds that we'd need 0.45 square kilometers for an omnivorous and balanced diet. Now, our 5 starships have a surface area of about 1% of that. So we'd either need to send 500 starships just to feed our crew, or find a way to produce food more efficiently. That 0.45 square kilometers is dominated by the space for raising livestock, so burger night might be the first thing we have to cut. It's possible to get the required area down to 0.015 square kilometers if we grow nutrition-dense crops like sweet potatoes using our best hydroponic or aeroponic systems. That's just 30 starships worth of farm, so we're back to the realm of the sane. The crew is also going to need some protein. Now, maybe we can get the quantity and variety from an efficient veggie protein source, especially with a little genetic tinkering. But if not, there are plausible meat options. Now, lab-grown meat technology is a bit speculative at the moment, but there is a very well-established carnivorous option suited to the less squeamish interstellar traveller. I'm talking about insects. For example, mealworms can be farmed at high densities and provide extreme protein richness. 1 to a few starships worth of mealworm farm might do the trick. Overall, we're going to need something like 6 to 10 times our crew's living space for food production. And that's for a pretty boring and slightly crawly diet, but maybe there are some gourmet yam and grub recipes just waiting to be discovered. A bigger challenge than food is the water, which our travellers need in order to grow that food and also in order to just live. An adult human needs around 2 litres of water per day, give or take. 500 humans need 1,000 litres per day. That's a cubic metre weighing a metric tonne. Our 140-year journey may be able to haul the required 50,000 tonnes of water, just barely, but forget about it for our 6,300-year slog. In either case, we're going to want a very good water recycling system. Just recently, the ISS reached a new milestone of 98% water recycling efficiency. Now, if that's as good as we ever get, then for our fast mission, we need a more reasonable 50-tonne supply of reserve water, perhaps 1 starship worth of water storage in terms of volume. But for our 6th millennia mission, we need 50 times that. So our generation ship just doubled in size just to haul enough water. And remember that we haven't even considered the water used and lost for growing food. Maybe add as much water again for 100 starships in water. In order for the long trip to be plausible, we may need to focus on improving our water recycling. Get it to at least 99.5% efficiency, which brings the reserve storage requirement down a factor of 4 to a similar scale as our farm requirement. There is perhaps one upside to needing to store all this water, and that's that the water can double as radiation shielding. About 1 meter depth of water surrounding habitats is enough to stop most dangerous space radiation. This is a solution that's being considered for trips to Mars, but would work well for a non-relativistic interstellar trip. By the way, this is an upside of travelling relatively slowly. Relatively minimal shielding is sufficient, and also bumping into a single dust grain isn't going to kill us. The last ingredient to add to our ship's biosphere is breathable air. Just as with water, recycling is critical here. The ISS currently uses a system designed by the European Space Agency called the Advanced Closed-Loop System, which recycles carbon dioxide back into breathable oxygen with around 50% efficiency. That's not nearly enough for a generation ship because huge supplies of fresh oxygen would be needed to replenish the losses. Instead, we'd probably need to rely heavily on our natural CO2 recyclers, the plants that we're growing for food. There have been various efforts to build self-contained biospheres capable of sustaining a breathable atmosphere, Maybe the most famous is the Biosphere 2 project, which did okay, all things considered. Yes, they had to install artificial CO2 scrubbers to help the plants, but the project at least demonstrated that a combination of natural and artificial systems could maintain a breathable atmosphere for some time. We have a few decades to perfect this, so there's a good chance that we can come up with an air recycling system that will work over long timescales. So maybe we can keep our crew alive and physically healthy for centuries or even millennia, but will they be happy and will they stay sane? The sense of isolation on such a long voyage will likely be a major challenge for maintaining the mental health of the crew. We need them to feel connected to Earth, to be part of something grander than their janky little spacecraft on its long journey. The first generation in particular will want to stay connected to their loved ones, but the two-way light travel time between the ship and the Earth will increase over the journey, ultimately reaching a lag of nearly 8.5 years near the end. NASA has done some tests to mitigate the dread that could follow from such separation from our home world. One solution would be the use of virtual reality. Crew members could find solace in digital 3D models of comforting and beautiful Earth environments, and in the case of Generation 1, their homes and loved ones. As the time lag increases, messages from friends and family and well-wishers could be recorded on Earth, beamed to the ship and played back in VR. On our cramped and sterile spaceship, it may be important to grant our travelers certain experiences that we on Earth take for granted. By improving the immersion and interactivity of our VR technology, we may be able to provide convincing visual experiences of mountains and sunsets, the auditory and even tactile experiences of wind and rain, and the olfactory joys of a forest or freshly cut grass. We can't build a Star Trek holodeck, but we can certainly push VR a lot further in the time before launch. Of course, the humans on the ship will still be humans. Arguments will happen, relationships will experience strain, and sensitivity and frustration levels may be heightened due to the isolation and confined spaces. And yet a high level of synergy and teamwork is needed for the mission to succeed. Sometimes a stressed human needs another human, but maybe when tensions rise and trust wanes, it will be helpful to have a trusted third party, one to give advice, to confide in, and to overall receive encouragement from. Someone that remembers and learns from the problems of past generations. Maybe we need an AI therapist. NASA has already piloted such a tool named Simon 2.0, the therapy AI robot. Preliminary testing seems promising and is generally agreed that some sort of tool or AI of this form could be very important for the success of a long-term space mission. Our plan so far will hopefully get our crew to Proxima B in good health, genetically, physically, and mentally. But how do we make sure that the mission of the launch crew is still the mission of the landing crew? How do we ensure that the knowledge and skills needed to complete the mission are passed across generations? Or that we preserve the wealth of cultural knowledge and tradition of these once Earthlings? This is where things get more speculative, as there isn't much research to go on. We just know that this stuff is going to be very important and probably very tricky. The shipbound society is going to need a culture and social structure that balances different needs. That structure needs to enable efficient operation of the mission, which may mean clear hierarchies in each operational area, but the culture also needs to promote crew happiness, otherwise we have a revolution in a generation or two. So, an efficient and stable social structure that somehow also promotes mutual respect, individual freedoms, and all the various values that we want this new branch of humanity to carry forward. Overall, it seems at least possible to build a generation ship that can reach Proxima B and to launch in the not too distant future. There are so many things that we know could go wrong, and no doubt many more unknown fail points. And the longer the mission, the more the risk of unexpected disaster. So maybe we really should focus on getting fusion on track. But it's encouraging to think that this sort of sci-fi endeavour is at least within our grasp if existential need or our adventurous spirit compels us. We are the middle children of history, but perhaps we're ready to grow up. Perhaps soon our generation ships will slip the bonds of gravity and distance to explore the new frontier of interstellar space-time. Hey everyone, if you enjoyed today's episode, then I highly recommend you check out the new feature-length documentary, Space, The Longest Goodbye. The film explores the reality that NASA's goal to send astronauts to Mars would require a 3-year absence from Earth, which would be twice as long as the current record for consecutive time in space. Bridging the gap between the astronauts who dream of space travel and the psychologists whose job is to keep astronauts mentally stable in outer space, the documentary vividly displays how those who dream of space travel must balance their dream of reaching new frontiers and the harsh psychological realities of space. The film is now available on YouTube, so check out the link below. After June 4th, it will be available exclusively on the PBS app.